example 2 in the notes, where we had some line. We were given the equation for a line in 3D space. And we were given the coordinates for some point called S, which had coordinates 1, 1, 5. And we were asked for the perpendicular distance between that point and the line. So that distance D there. So last day we used method number 1, where we made use of the dot product. And we found that the correct answer D was equal to root 5. So I want to quickly look at a couple of other methods today. Let's look at method number 2. In method number 1, we made use of the dot product to find the projection. We found some other point on the line, point P, from the line equation, 1, 3, 0. And that allowed us to draw a vector from P to S, call it PS. And then we used projection we projected that vector PS onto the vector V, which we get from our line equation as well. Okay, V is simply equal to 1, negative 1, 2. They're just the coefficients of the parameter T in the line equation. So we found the projection of PS onto V, which is in the same direction of the line. So we found this distance and then found this distance using vector addition. Found this vector, we know this vector subtracted from that vector gives us that vector, and the magnitude of this vector is obviously the distance we're looking for. Well, instead of projecting onto the line L, what if we project onto a vector that is normal to L, like that? A vector n. Okay, so it is normal to this line. Okay, so if we find the projection of this vector now onto this vector, that's going to give us this distance, right? If we put a light here shining this direction, then the shadow caused by this on this line defined by this normal vector is going to be this distance here. This is the shadow of this due to a light here shining in this direction. So it's a little bit more of a direct method. We're going to find the distance D then simply is going to be equal to the projection of PS onto n hat. Remember, whenever we calculate a projection, the second vector has to be a unit vector. So n hat is the unit vector of this vector n, which is perpendicular to the line like this. Okay? Well, we know that this n must be perpendicular to this v. Okay, n must be perpendicular to v, and therefore n dot v, their dot product, must be equal to 0 if the angle between them is 90 degrees. Okay? Okay, well, we have to find this vector n, and let's say n just consists of 3 components, n1, n2, and n3. So that means n1, n2, n3 dot 1, negative 1, 2 has to be equal to 0. Okay, so that when we do that dot product, we get n1 minus n2 plus 2n3 is equal to 0. Okay, well, we've got one equation and 3 unknowns. Obviously, there's an infinite number of solutions. There's an infinite number of vectors n which are perpendicular to this line, because that perpendicular to v, which is parallel to the line, so there's an infinite number of vectors n that are perpendicular to the line L. Well, why is that? Well, I'm drawing things in 2 dimensions here, but you can imagine this vector n, if I fix its tail here to the line, I can spin this vector around the line and there would be an infinite number of vectors n that would be parallel to this line L, right? If the tail is fixed to L here and I just spin it, it's hard to do in over zoom, but you take it and you spin it around the line like this, there's an infinite number of vectors n that would be perpendicular to this line L. In addition, there's an infinite number of, I didn't have to draw n here, I could have drawn n over here, or I could have drawn n over here. Okay, you take each of those and spin them around the line. Again, there's an infinite number of vector n. So we've got an infinite number of solutions for n. So we've got to constrain things a little bit more. Well, which n are we looking for in particular in order to do this projection up here to get this distance d? Well, obviously, whichever one of these three n's we choose here, we have to choose, we can't just choose any n that spins around like this. We have to choose the n that is in the same plane as our line and this point S. Okay? And it's the one that I've drawn. This looks like it's in the plane of my iPad here, which is exactly what we need, right? I wouldn't want this n vector to start here and to go straight into the page. That vector would be perpendicular to the line L here, but it would not be in the same plane defined by the line L and the point S. Or another way to think of it is, I need this vector n here to be in the same plane as this vector ps. Okay? Well, for that, how do I define that? Well, I've got ps and I've got v. Okay? If I take ps cross v, what do I get? I get a third vector that is perpendicular to both of them. Right? And if you use your right hand rule and you curl the fingers of your right hand from PS to V like this, your thumb is going to go into the page or into the screen, okay? So if I take PS cross V, I get a third vector that goes into the screen at this point, okay? That vector is perpendicular to this vector that n that I'm looking for. Okay, remember, if I take this n here and I fix its tail to the line, I can spin it around the line here to get an infinite number of vectors that are parallel to the line, or pardon me, perpendicular to the line. One of those is going to be the vector I get when I take PS cross V. It's going to be the one going straight into the page. Okay, that obviously is going to be perpendicular to this n, which I'm looking for, which is in the same plane as the page. Okay, so PS cross V goes into the page. The particular n I'm looking for is in the plane of the page. So that means the n I'm looking for, if I take its dot product with this PS cross V vector, which goes into the page, I want those to be 90 degrees apart, so I need their dot product to be equal to 0. Okay? So that is going to stipulate, that's going to be an additional constraint that is going to give me one of these particular ends, not any one of them that spins around here, but the one that's in the plane of PS in the line. Okay, well, you can do PS cross V simple enough. That's just a cross product. If you do use the determinant method, you will quickly get 1, 5, 2. Okay, so that's this vector that's going right into the page, and it needs to be, when I take its dot product with this n that I'm looking for, that has to result in 0. So my n1, n2, pardon me, n3 vector dotted with this ps cross v has to be equal to 0. Which means I get a second equation, that's n1 plus 5n2 plus 2n3 has to be equal to 0. So now I got two equations. I got this one up here, and I got this one down here. So I could, for instance, I could difference those equations. Equation 1 minus equation 2 will give you 6n2 equal to 0. Which means that n2 is equal to 0. Okay, so that means we end up then with n1 plus 2 n3 is equal to 0. right? If we put n2 equal to 0 either into this equation or into this equation, we end up with n1 plus 2n3. n1 plus 2n3 is equal to 0. Okay. All right, well, you'll look at this and you go, oh, well, still one equation, two unknowns. Well, if we think about what we did with this second constraint here of, where is it here? Taking PS cross V and making it the dot product of that with n equal to 0, all we did was we said, okay, we're going to, equation 1 said we're going to find a vector normal to the line. Equation 2 was, well, which one of the vectors normal to the line that spins around the line? Well, the one that goes right into the page. And now we're left with, well, we still have an infinite number of solutions. Well, because we could draw an infinite number of vectors n, that goes straight into the page. I could draw it there, 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 right? I've got an infinite number of vectors n that start on the line L and go straight into the page. Well, which one do I want? Pardon me, I misspoke. The vectors going into the page are PS cross V, okay? N is in the plane of the page. Sorry about that, okay? PS cross V is into the page. Well, I've got an infinite number of those too that I could have used. But really what we're looking for is this n vector. By doing this here, we just made sure that we're choosing an n vector in the same plane as the page here. Okay, but we've got an infinite number of n vectors that are in the plane of the page. Or I could draw them this way. Right? There's an infinite number. Well, which one do you want to choose? Good news is it doesn't matter. Any one you choose will work. Okay? So we can choose any value of n1 and n3 that satisfies equation 3. That equation there. So pick whatever you want. Well, make n1 equal to 1, in which case n3 has to be equal to negative 1. Pardon me, that doesn't make sense. n1 equal to 2, pardon me. If we make n1 equal to 2, n3 would be equal to negative 1. Or I could make n1 0, in which case n3 also has to be 0. Or I could pick any combination of n1 and n3 that satisfies equation 3. That will give me a normal vector which will be in the which will be in the plane of this page and will be perpendicular to the line L. Okay? So there's more than one right answer because we know that for a line in 3D space there's an infinite number of answers. Okay, so when you do that, that means now we've got n is equal to 2, 0, n2 is equal to 0, and n3 is equal to negative 1. So there's a vector n that will work for us. So to do projection, we need the unit vector. So 1 over root 5 times 2, 0, negative 1 would be a unit vector. And now the distance we're looking for is the magnitude of PS projected onto n hat. And PS was 0, negative 2, 5, dot 1 over root 5, 2, 0, negative 1. Equals root 5. Same answer. Okay? And something you can do is try a different value of n, and you should get the same value d. Okay, so that's method number 2. All right, let's go back here. Let's look at a third one really quickly. If we go back to what we're given in the question, we're given this point S here, and we're given the equation of our line, which gives us this point here, 130, or just 130 from the line equation, right? These are the points of a coordinate, the coordinate of a point on the line. We know a vector parallel to the line, again from the line equation, the coefficients of t. So we can draw this vector PS, and we've got this vector V, and we said, well, what's the cross product? We could find the cross product of two vectors, because we know two vectors. So what if we use just that cross product directly? What would that give us? Well, if we just, sometimes you just got to look at what you're given and say, well, I got two vectors. What if I take the cross product of those two vectors? Well, what's the cross product? It's the magnitude of PS times the magnitude of V times the sine of the angle between them, okay, times some n hat, which gives us the direction of that vector from this cross product. Well, if we're not so much interested in getting a vector, we can say, what's the magnitude of that vector? Which means we're done writing there, right? We don't have to worry about writing an n hat here at the end. Okay, well, what does this give us? We know a vector, the vector PS, we know the vector V, so we can find their their cross product using the determinant method. So we can get a number for the left-hand side of this equation. We can also find the magnitude of PS. We can find the magnitude of V, which means we can find the angle of theta. If we go back, and what are we dealing with here? There's our line L, here's our point P, S, here's our point P, right? Here's the vector PS. Here's the vector V. That should be parallel to the line. Okay? Or I could draw V like this. V could be on the line. I can find this angle theta. Okay, well, I can draw this right angle triangle again because I'm looking for this distance D. Simple geometry tells me that D is what? Or the sine of theta is equal to the distance D over the magnitude of PS. Right? Just simple trig. Which means D is equal to the sine of theta times the magnitude of PS. So if I rewrite this here as V times PS sine theta, well, this part here is D. So if I rewrite that equation, D is equal to the magnitude of the cross product, PS cross V, divided by the magnitude of V. I know PS, I know V, I can find all of these things, right? PS cross V, if you do that, you'll find that's 152, divided by the magnitude of V, which is what? What was V again? Where's my V vector? V itself is equal to 1, negative 1, 2. We get that from the line equation. So 1 plus 1 plus 4, root 6. Magnitude of 152 divided by root 6 will give you 25 plus 4 is 9, root 30 over root 6, which is, again is root 5. So we get the same answer again. Okay? Okay, and there's a fourth method in the notes if you want to look at it, but I think we've beat that problem pretty much to death. Any questions about that one? Okay, let's do another relatively simple one, and then we'll do the cat and the mouse problem. So in the lecture notes, this is example 4. So if we are given a plane, x plus 2y plus 4z is equal to 7. And we're given 2 points. Point Q0, which has coordinates -1, 2, 2. And Q1, which is given 1, 3, -1. So 2 points in space, and we got a plane. Well, can we tell whether these 2 points are on 2 points on the same side of the plane? Or are they on opposite sides of the plane? Or do we just not know? So we've got a plane in 3D space. I don't know what it looks like, but I'm just going to sketch it like this. And again, it goes to infinity in each direction. So I'm just drawing part of it. And we want to know, well, are Q0 and Q1, are they on the same side of the plane? Or are they on opposite sides of the plane? And then if they're on opposite sides of the plane, what's the point of intersection of the line that connects those two points with the plane? What's this intersection point where that line connects, if they are in fact on opposite sides of the plane? Well, in order to solve this, all we got to do is we have to plug these xy coordinates of each of these points into the plane equation. If, let's say Q0, we take its coordinates and we plug them into this plane equation, if they actually satisfy the equation, which means we get 7 on the left-hand side here, when we put -1 in for x, 2 for y, and 2 for z, well, that means point Q0 is on the plane. Okay? But if these coordinates do not satisfy this equation, well, then Q0 is not on the plane. It's on one side of the plane or on the other. So let's try that. Q0 into plane equation. What do we get? We get -1 plus 2, 2 times 2 plus 4 times z, which is 2, right? And what do we get? We get -1 plus 4 plus 8. We get 11. 11 is obviously bigger than 7, which is what it should equal if this point is on the plane. So obviously Q0 is not on the plane. It's on one side of the plane or the other. Okay, let's take coordinates for Q1 into plane equation. So coordinates Q1 are 1, 3, -1. So that's 1 plus 2 times 3 plus 4 times -1. And what do we get? We get 1 plus 6 minus 4. 6 minus 4 is 2 plus 1. We get 3. Well, that's less than 7. Again, it's not equal to 7, so point Q1 is not on the plane. It's on one side of the plane. Well, just you can do the same thing in 2 dimensions, right? If you were just working in 2 dimensions and you had a line, right, y is equal to mx plus b, and you took a point on this side, its coordinates, x1, y1, and you took a point here, x0, y0, on opposite sides of the line, you can do the same thing. You can plug this into here, and you'll find that it will not satisfy this. But if I rewrite this as b is equal to y minus mx, right? If I put these coordinates in here for x and y, I'll get a value which is different from b, probably bigger than b. If I take these coordinates, put them in here, again, they'll not equal b, I'll get a value less than b, which tells me that these 2 points are on opposite sides of the line. Same thing here with a plane. I found that when I put the coordinates for Q0 into the plane equation, I got a number here on the left-hand side which was bigger than 7. When I put these coordinates in, I get a number less than 7, which means they're on opposite sides of the plane. Okay, so we know they're on opposite sides of the plane. If they both turned out to give a number greater than 7, then they're on the same side of the plane. Or less than 7, then if they're both less than 7. Okay, well, can we find this intersection point Q? Yep, we can. It's just 2 points in space. Okay, we know the coordinates for Q0 and Q1, so we can find the line equation for that, right? That's what we one of the types of problems you can do in line with the line equation. You know the coordinates for 2 points on the line. You can easily find the line equation, because what do you need to write the line equation? You need a point on the line. Well, you got two, Q0 and Q1. You can use either one. And you need a vector parallel to the line to write the line equation, right? Well, I can find that. Obviously, I can find the vector pointing from Q0 to Q1. That would give me a vector parallel to the line. Or I could find the vector pointing from Q1 to Q0. Also a vector parallel to the line. So you can do that and write a line equation. Again, there's a number of different line equations all representing the same line. Any one of them will work. But if you do that, you can find that the line that connects Q0 to Q1, -1 plus 2t, -1 plus 2t, y of t is equal to 2 plus t, z of t is equal to 2 minus 3t. Okay, so that's an equation for the line. Obviously, the point that was used, you need a point in a vector parallel to the line. Obviously, the point that was used was -1, 2, 2, Q0 when we wrote this, right? -1, 2, 2. And this vector 2, 1, -3 is just the vector between Q0 and Q1. Okay, so there's our line. Okay, well, we want to find the point Q where that line intersects the plane. We got an equation for the plane, we got an equation for the line. For a point on the line, there's only one point on this line that is also on the plane. It's this point here, the point of intersection Q. So we're looking for the point on the line that is also on the plane. Okay, well, the xy coordinates of points on this line are given by these expressions here, which means these three expressions, this for x, this for y, this for z, must satisfy the plane equation at the point we're looking for, right? This point on the line has to satisfy the plane equation for this one point here that's on the line and on the plane. The coordinates of this point Q, they have to satisfy the line equation and the plane equation at the same time. So all we have to do is put the line equation into the plane equation. Okay, so the plane equation was x plus 2y plus 4z is equal to 7. Okay, well, what is x on the line? X is equal to -1 plus 2t. -1 plus 2t. Plus 2 times y. Well, on the line, y is equal to 2 plus t. 2 plus t. Plus 4 times z. On the line, z is equal to 2 minus 3t. Okay? So the things in the parentheses are the x, y, z coordinates of a point on the line. They're equal to these. That's got to be equal to 7 for that point to also be on the plane. Okay? The coordinates of this point on the line must satisfy the plane equation for this point Q that's both on the line and on the plane. So one equation with one unknown t, you solve that for t, and you end up with t equal to 1/2. You put 1/2 into t in each of these three here, and you get values for x, y, and z. So x for t equal to 1/2 is going to be equal to 0. Y for t equal to 1/2 is going to be equal to 5/2. Z for t equal to 1/2 is going to be equal to 1/2. So the point Q has a coordinate 0, 5/2, 1/2. Okay? All right. A couple of things to think about on your own time. What would happen if this line that connects Q0 and Q1 is actually parallel to the plane? What would happen if, in this method that we used, if Q1 was over here on the same side as Q0 and parallel to the plane? Or what would happen if the line was in the plane? Okay? Talks about that a little bit in the lecture notes. You can look at that yourself. Okay, we have to move on. Any questions about this example, though, before we move on, the way we did this? Okay, so the last example we want to look at here, which is the cat catching the mouse problem. Just to keep things interesting, we're gonna keep it in 2 dimensions. Okay? So let's say we've got a cat, and we are told that the velocity of the cat, the cat travels along a straight line, defined in 2 dimensions like this, -4 plus 2t. We're just going to keep it in 2 dimensions just to make things a little simpler. 7 minus 3t. Now, once we're in 2 dimensions, we could just have a line equation y equal to mx plus b, but we're going to keep it using parametric equations because that's what we've learned for lines in 3D space. And we've got a mouse that is traveling along a straight line trajectory defined by x equal to 1 plus t and y equal to -6 plus 4t. Okay, so we've got a cat traveling on a straight line, we've got a mouse traveling on a straight line, and we are asked, or we're told that they're both traveling at a constant velocity. Okay, so neither one can dictate or deviate from their straight line trajectory, and they can't change velocity halfway. They're traveling at a constant velocity, and the question is, well, will the cat catch the mouse? Well, if they're both traveling on straight lines at a constant velocity that can't change, and the straight line can't change, what has to be true for the cat to catch the mouse? Well, their trajectories have to cross at some point in space, and the cat and the mouse have to be at that intersection point at the same time. If both of those things are true, if their trajectories cross, and if the cat and the mouse both occupy that intersection point at the same time, the cat's going to catch the mouse. If either one of those is false, then the cat's not going to catch the mouse. The mouse might have crossed the trajectories, passed through that crossing point first, or maybe the cat went through it first, and then the cat doesn't catch the mouse. But for the cat to catch the mouse, the trajectories have to cross, and the cat and the mouse have to both be at that crossing point at the same time for the cat to catch the mouse. So our task is, well, do these two lines cross? And if they do the cat and the mouse occupy those at the same time t? Do they occupy the crossing point at the same time t? Okay, well, how do we determine first of all if they cross? Well, from the line equations, we can write a vector parallel to the trajectory, and say for the cat, let's call it v1. That is simply going to be equal to what? It's the coefficients of your parameter t, so 2 minus 3. Okay, so that's a vector parallel to the trajectory of the cat. A vector parallel to the trajectory of the mouse is going to be 1, 4. Okay, those vectors are parallel to the trajectories. So if the trajectories cross, these two vectors have to cross. Or if the two lines, the two trajectories are parallel, which means they never cross, these two vectors would also have to be parallel. Are these two vectors parallel to each other? That means, is V1 a scaled version of V2? Is there any number I can multiply V1 by to get V2?
No.
No, which means they are not parallel. Oh, pardon me. Which means the two lines, the two trajectories of the cat and mouse are going to cross, right? They're not parallel, so at some point they got to cross. So the trajectories intersect. Okay, so far so good for the cat, right? At some point the trajectories are going to cross. Well, in order for the cat to catch the cat and the mouse both have to be at that crossing point at the same time. Okay? Well, that means that the cat's coordinates xy have to equal the mouse's coordinates xy for the same value of t. Right? T is time. We're going to interpret t as time. So for one value of t, the same value of t for the cat and the mouse, if the cat's coordinates xy are the same as the mouse coordinates xy, cat catches the mouse. They're both there at the same time, right? So if we do that, that means the cat's x coordinate, -4 plus 2t, must be equal to the mouse's x coordinate, 1 plus t. Okay? This is x cat, this is x mouse. Okay, if we do that, we find t is equal to, it's just one equation with one unknown t. We find t is equal to 5. Okay? Likewise, we have to make the cat's y-coordinate equal the mouse's y-coordinate. And the cat's y-coordinate is 7 minus 3t. That's got to be equal to the mouse's y-coordinate, which is -6 plus 4t. And if you do that and solve it for t, we get t equal to 13 over 7. Okay, well that's not 5. Which means that the cat's x-coordinate and the mouse's x-coordinate are equal when t is equal to 5. And the cat's y-coordinate and the mouse's y-coordinate are equal at a different time, t equal to 13 over 7. So that means what? That means that the cat and the mouse aren't at the same coordinates x and y at the same point in time. Okay? So the result is cat does not catch the mouse. There is no one-time t when the cat's x-coordinate equals the mouse's x-coordinate and the cat's y-coordinate equals the mouse's y-coordinate. Therefore, the two lines cross, but the cat and the mouse don't occupy that crossing point at the same period of time. So too bad for the cat. Okay, well, where do these two lines intersect? Can we find that? Yes, we can. We've got the line equations here. We should be able to find out what coordinates x, y these two lines cross. Where do the trajectories cross? Well, we're going to rewrite these line equations using different parameters this time, okay? The cat, x1 we're going to use a parameter of s. Oh, pardon me, 1. So this is for the cat. It's the same line equation. It's just, instead of t, I'm using s for the parameter. Because the parameter can be anything we want it to be. And for the mouse, I'm going to rewrite its equations, and I'm going to use k for its parameter. Not 3, 2. Okay, same equations as we had before, but I'm going to use different parameters for the cat and the mouse. I'm going to decouple them. So we're not going to think of the parameter as time anymore. It's just a parameter. When that parameter changes, the xy coordinates of the cat change one way, and when k changes, the parameters of the mouse change according to its line equation. So we're going to decouple the cat and the mouse. Treat them independently. Use different parameters. Okay, well, our objective here, we're trying to find where these two lines cross. So what we want to find are the values for s and k such that x1 equals x2 and y1 equals y2. Because that's the crossing point, the intersection point, where the x coordinates are equal and the y coordinates are equal. We want to find the values for s and k that make that true. Find values for s and k such that x1s equals x2k and y1s equals y2k. That's what we need to do to find the crossing point. Well, we just say, okay, well, x1s is pardon me. We just say x1s, which is negative 4 plus 2s, has to be equal to x2k, which is 1 plus k. Okay? Negative 4 plus 2s has to be equal to 1 plus k at the crossing point. So you rearrange that equation and you, well, we're not going to rearrange it here. And we're going to make y1s, which is 7 minus 3s, equal to negative 6 plus 4k. Okay, those are the y coordinate of the cat has to be equal to the y coordinate of the mouse at the intersection point. So, two equations, two unknowns. We can solve it, right? Gaussian elimination, or however you want to do it. Right? That's high school stuff, or at least first year stuff, so everybody should be able to do that. And when you do that, you'll find values for s and k to be s equal to 33 over 11, which on most days is just equal to 3, and you find k is equal to 1. Okay? Two equations, two unknowns, we find the values for s and k. So that means when s is equal to 3 and k is equal to 1, the x and y coordinates of the cat and mouse trajectory are equal. Okay? So, and we can say now, well, you know, if s is time for the cat and k is time for the mouse, obviously we see that they're at the crossing point at different times, which we already knew. Okay? We found that out already before. This just confirms that. So now we put k equal to 1 into here, and we've got the coordinates, or we put s equal to 3 into here. Either way, we'll get the coordinates x, y at the crossing point. Either way, we should get the same answer. It's a good check. If you don't get the same answer, you've done something wrong. Either way, you do that and you find that the xy coordinates you get are 2 to negative 2. Okay, so this is the intersection point. Okay, so we found the intersection point of the trajectories. We know that the cat and the mouse don't occupy them at the same time, so the cat doesn't catch the mouse. Okay, well, we want to help the cat out here. So what can we change so that the cat does catch the mouse? Well, we're going to have to change something. One thing we could change the speed of the mouse. Pardon me, of the cat. Well, we could change the speed of the mouse too, but cat's trying to catch the mouse, so maybe the cat changes its speed. Doesn't change its trajectory. Crossing point is still the same. The intersection point's the same. Their trajectories are the same, but maybe the cat, if it got to the crossing or the intersection point after the mouse, well, maybe the cat has to speed up. Or if it got there before the mouse, maybe the cat has to slow down, right? So we're going to change the speed of the cat. But we know that for the cat to catch the mouse, it's going to do it at the intersection point, which we found to be 2, -2. This still stays the same, right? The intersection point stays the same, the trajectory stays the same. All that's going to change is the velocity of the cat. Well, that vector that's parallel to the line of the trajectory of the cat, we can interpret as the velocity. So maybe all we have to do is change the velocity, the vector that's parallel to the line that the cat is following, right? So the direction of the trajectory of the cat, we call that v1 up above. Okay. We could turn that into a unit vector. Just divide it by its magnitude. That gives us a unit vector in the direction of the cat. Okay, it has a magnitude of 1, so it's telling us the direction of the velocity, which is the trajectory of the cat. But it doesn't tell us anything about the speed of the cat. Okay, we know that velocity vector v1 up from the line equation, and we can divide it by its magnitude, which is root 13. And 2 minus 3, 0 was the value of v1, right? You divide it by its magnitude, we now have a unit vector in the direction that the cat is traveling. Okay, well, we want a new velocity vector for the cat, which is going in the same direction. Cat's still going in the same trajectory, but it's got a different speed, so it's going to have a different magnitude. So multiply it by some value c, not the speed of light, but just some magnitude c, times this unit vector, which is the direction that the cat is traveling, right? That gives us a new velocity vector for the cat. So now the parametric equations for the cat are going to be x equal to -4, y equal to 7. That's the same, -4 and +7. If we go back up to the original line equation for the cat, pardon me, right? -4, -7, still the same. We're going to be changing this part now, though. The velocity vector is no longer 2 minus 3. It's going to be c times this unit vector, which we write out plus c times 2 over root 13 for the x part, times the parameter t, minus c3 over root 13 for the y. Okay, and obviously we're in 2 dimensions, which is why this is 0. I just wrote 0 there because if it was 3 dimensions, but we're working in 2 dimensions, so the z coordinates are obviously 0. Okay, so this is the new line equation, or line equation for the cat. Okay, it still defines the same line. Remember, there's an infinite number of ways to write the line equation for a single line. All that's changed is the vector parallel to the line. We've made the magnitude of that vector different. Okay? It's still the same, it's still a vector pointing in the same direction. It's still parallel to the line. It's still the same line, but it's just a vector with a different magnitude because we're taking that vector to be the velocity, and by changing its magnitude, we're changing the speed of the cat. But the cat's still going in the same direction on the same line. Okay? Okay, well, we need to find what the appropriate value of C is so that the cat occupies the intersection point at the same time as the mouse. Okay? Well, we know the intersection point is 2 minus 2. Okay, well, when does the mouse reach that intersection point? If we go up to its equation, way up here, and you substitute a value for x of 2 and y of minus 2, you can solve for t, right? With either one of these equations. You put a 2 in here, you put a minus 2 in here, you'll get the same value for t. So if you put this intersection coordinates into, oh, I'm going over time. Pardon me, I'll stop here. We find that t is equal to 1. Okay? So now we know the mouse is at the intersection point at the time t equal to 1. You put t equal to 1 into here, and you find for x equal to 2 and y equal to negative 2, because the cat has to be at the same coordinate times, and you find that t is equal to, or you put t equal to 1 in there, and you find that c has to be equal to 3 root 13. Okay, so that means our new velocity vector for the cat is equal to c times the old one, which is equal to now 6 minus 9. And now the cat will catch the mouse because it's at the crossing point 2 minus 2 at the same time of t equal to 1. Okay, pardon me, I went over time by a few minutes. We'll stop there and we'll pick it up on Monday. Have a good weekend, everyone, and look out for assignment number 1. I can answer any questions for a minute or two if anyone has one.